Yeah, so the first thing I want to talk about is the midterm we have just finished, right? So I'm sure all of you have still remember the midterm, and let's see, please. Okay, and I just want to really quickly go over what's the solution for the midterm. A lot of you got it correctly, so. Basically, the first question is almost trivial, right? So it's kind of a question to give you some hint, basically to get you started. So we have the differential equation du dt equal to a matrix 0, 1, a, b times u. So u is a vector of two components for sure. And if you plug in forward Euler, the scheme would be u of n plus 1. Of course, the time discretization is going to be un minus 1 divided by minus un divided by delta t. And the major difference between forward Euler and backward Euler is the right-hand side. Instead of plugging in un plus 1 for backward Euler, we have un for forward Euler, right? So that's basically question one. And to actually implement it, of course, you need to keep the unknown on the right-hand side and move everything else to the right-hand side. Okay, so question two, we need to start thinking about two things. One is, the question is, in what situation would forward Euler be a good choice for this particular equation? So there are two aspects. One aspect is know what kind of equation forward Euler is stable for, what kind of equation forward Euler is not stable for, right? And the second is forward Euler being a explicit scheme would not be a good choice for solving stiff equations. So we really have two aspects. Aspect one is stability. Okay, so many of you have correctly figured out what is the eigenvalue of the matrix 0, 1, AB. And the eigenvalues, if you plot it out, if you basically, the correct way to calculate it is to solve this equation. The determinant of 0 minus lambda, 1, A, B minus lambda, right? So basically subtract lambda times identity from the matrix. And the determinant has to equal to 0. So you reformulate that into a quadratic equation, and or you can just solve use MATLAB, right? So either way, you get b plus minus square root of b squared plus 4a divided by 2. Okay. So one thing you can see is that this is the eigenvalues of the matrix that is inside the ordinary differential equation. So you know that the ODE itself would be stable if the real part of this eigenvalue is negative, right? So several of you were a little bit confused in the beginning about the stability of a differential equation versus the stability of an iteration. So there is a difference when you write this down as a differential equation, du dt equal to matrix times u, versus an iteration, which is un plus 1 equal to a matrix times u, right? So having a differential operator on the left-hand side actually changes things. So the stability for the differential equation, the stability region for the differential equation is not the unit circle, it's the entire left plane, right? If it's an iteration, the stability region would be a unit circle. If it's a differential equation, the stability region is actually the whole left plane. So if you solve the equation analytically, the stability region of the ODE, that's shaded in blue, would be the entire left plane. Okay, now if we switch to forward Euler, we know forward Euler is actually not going to be stable for everything the ODE is stable for, right? That's actually true for all ODE integration schemes. So forward Euler is stable in a circle that's centered at -1 over delta t, and with a radius of 1 over delta t. So essentially, as you decrease delta t to 0, and only when you decrease delta t to 0, the forward-Euler stability region would approach the stability region of the analytical ODE. Okay, and in particular, there are points in the stability region of the ODE. These points are actually exactly on the imaginary axis. If you have a point here or here, then no matter how small delta t is, it is not going to be within the stability region of forward-Euler, although it is in the stability region of the analytical ODE, right? So basically, in these cases, forward-Euler is not a good choice. I mean, these are the cases where the behavior of the ODE would be just oscillating without decay. But if you solve it with forward-Euler, it would still oscillate but would grow. Okay, so in this case, because we already have a formula for lambda, you know that in order for forward-Euler to be stable, at least for small enough delta t, we have to have B, which is the really the averaged real part of these eigenvalues. So B has to be strictly less than 0, right? So this is really the scenario. So B has to be strictly less than 0 if B squared plus 4A less than 0. So basically, if we have a complex pair, then the real component has to be less than 0. So this is condition 1. This is condition 1 for forward-Euler to be a good scheme. The second condition is stiffness, right? And we know an equation would be stiff if the ratio of the eigenvalues are very large, on the order of 1,000, for example. The equation would be stiff. Okay. And now if we look at, again, the formula for the eigenvalues, if the eigenvalues are a complex pair, then the magnitude of these eigenvalues are actually exactly the same. So there is no way the equation is going to be stiff. The equation is only going to be stiff if it is actually a pair of real eigenvalues. That means the stiff case is actually different from this case, right? So the condition is different. When we have a pair of complex eigenvalues, the condition for which forward-Euler is a good choice is this. But when B squared plus 4A is actually greater than 0, the condition for forward-Euler is different. It is actually basically, if the condition is the following: my 4A, the magnitude of 4A has to be comparable to the magnitude of B squared. So this is basically excluding the case when the magnitude of 4A is much, much less than B squared. So if the magnitude 4A is much less than B squared, then what we get? So if 4A is much less than B squared, what we get is B squared plus minus pretty much B squared, right? Divided by 2, which is equal to either B or 0. In the case of minus, in the case of B is usually negative, right? So if it's plus, then what we get is a, since B is minus, if it's plus, we actually get a cancellation and we get almost 0. If it's minus, then we get basically B, right? So of course the 0 is not going to be exactly 0 because 4A is not going to be exactly 0, but this close to 0 means it is much, much less than the value of B. Okay, so essentially these are the two conditions when we have real or imaginary eigenvalues. All right, make sense? Any questions on this question?